Hello everybody, this is Mrs. Gilbert, and I am recording lesson 2, which is going to be separated into lessons 2A and 2B. It will be pages 6 and 8 in your interactive notebook. The first one on page 6 is the electromagnetic spectrum, lesson 2A. And I would first like to take this opportunity to go over the guiding questions, which are right here at the top. So there are 3 guiding questions for the electromagnetic spectrum. The first one is, what makes up an electromagnetic wave? The second one is, how are electromagnetic waves alike and how are they different? The third question is, what waves make up the electromagnetic spectrum? At this point, I also need you to make sure that you put your name at the top of your paper, your class, and the date. That is important. All right, don't forget to put page number up at the top. Again, this will be page 6 in your interactive notebook. I'm going to erase all my highlighting now. Okay. Now, first off, the electromagnetic spectrum. All right, the sun, we're going a little bit back to astronomy now. The sun emits energy in the form of the electromagnetic spectrum. Only part of this electromagnetic spectrum is visible light, which is what we can see. And if you look at this diagram, you see only a tiny portion of the middle of the electromagnetic spectrum is visible light. The rest of it, like radio waves, infrared, ultraviolet, X-rays, and gamma rays, we cannot see with our eyes. I will go back to the note sheet where it says the sun on your paper. There are 2 sets of bullets. You will write the information right here on those 2 bullets. So the sun emits energy in the form of the electromagnetic spectrum, and it is only part of it is visible light, what we can see. I am going to move on, but obviously if you need to pause here to write that down, go ahead and do so. The next part of our notes asks how the electromagnetic energy is transmitted. So I'm going to move to this page. Electromagnetic energy is transmitted in waves. And here I have a diagram of a wave. Okay? And I'm going to label my waves. So my first label is going right here. A wavelength is how long the wave is, and it goes from one point on the wave to a similar point on the wave. That is a wavelength, one full wavelength. Okay, and again, this diagram is on your notes. You have the same picture on your notes, so you should be labeling this as I go along. All right. The next, the crest of the wave is the very top of the wave. Okay. The trough of the wave is the very bottom of the wave. And the amplitude is how tall the wave is. Okay, and that actually goes from the middle part up to the crest, and that is the amplitude. And I'm not going to worry about those other words for right now, so I'm going to cover that back up. I'll give you a moment to make sure you have that written in. Okay, so again, you should have this here. Okay, moving on. The next part of your notes addresses the guiding question B, which is how are electromagnetic waves alike and how are they different? So over here on this page, I have the electromagnetic spectrum. And you have this on your notes as well, toward the bottom. Let me scroll down. Here we go. So you have this as well, but I'm going to have you write in some details on this. So let me go back. Okay. Now, you notice that a couple of things. First off, over on the left, we have radio waves. Over on the right, we have what are called gamma rays. And I want you to notice the shape of the waves as you go from radio to gamma rays. All right, and notice that the waves go from being very spread out to very close together. Okay, what's happening is that the wavelengths are going from being very, very long to extremely short over here at the gamma ray end. And down here at the bottom, it explains about the size, or what the wavelengths are about the size of. So wavelengths are about the size of, so for radio waves, it's about the size of buildings. So radio waves can be very, very long. Microwaves are about the length of grains of sugar, so quite a bit smaller. Infrared waves, which I will talk to you about what those are in a moment, those are about as long as protozoans. So those would be microscopic organisms. Visible light waves, the ones that we can see with our eyes, are the length of bacteria. Ultraviolet rays are the length of molecules, which we cannot see with microscopes, so that's even smaller. X-rays are about the size of atoms, again, extremely tiny. And gamma rays, the smallest of the electromagnetic spectrum waves, are the size of atomic nuclei, which we can't see with any kind of microscope. Very, very tiny. Now what I'm going to do is have you write in some descriptions of these waves up above. And I'm going to get rid of my white space here, my white. Okay. All right. And I'm going to bring this down. The magic of the whiteboard. Smart notebook. Okay. Now, on your note sheet, you have a white section above your diagram right here. This is the spot where you're going to write in that information contained in the bubbles. So right in here is where you are writing in the bubble information. And I will go over that. So first off, microwaves are waves that energize water molecules in order to heat food. Infrared waves are heat waves. Many of you perhaps have heard of infrared goggles so that you can see the heat that different things give off at night. They're like night vision goggles, okay? Visible light, again, is the light that you can see with your eyes. Ultraviolet light are waves that go through your skin, and those are the ones that give you a tan or a sunburn. But they're powerful and they have enough high energy to actually go through the cells in your skin and get into the DNA. But they can also, they change the melanin in your skin, which is what gives you the tan or the sunburn. X-rays are waves that, again, they have enough energy that they can go through your body tissues to the bone. And that is what allows doctors to be able to see your teeth or your bones in an X-ray. So we actually use the properties of X-rays in the medical industry. Gamma rays, those are produced from nuclear reactions. It's nuclear radiation, And this type of ray is so tiny and so powerful, such high energy, that it can go straight through our bodies. It's very, very dangerous because as it goes through our bodies, on the way through it, it can destroy our tissues, it can change our DNA. And then up here, so there's a little blurb, and it said, these waves are small enough and have enough energy to change your DNA. And when that happens, you have mutations. And when you have mutations, there's the potential for developing cancer. So overexposure to ultraviolet radiation, X-ray radiation, and gamma ray radiation, too much of these things can be very dangerous to living things because it does mutate our DNA, which then causes a potential for cancer. Not a good thing, obviously. Okay, so I'm going to scroll down, and there's another picture here. And you don't have this picture on your notes, but that's okay. Just another example. The big difference with this picture, though, is it's backwards from what's up here. Radio waves were on the left in this diagram, but down here, they're on the right. And I wanted to show you this because sometimes, depending on who's making the electromagnetic spectrum diagram, they might switch it around the opposite way. That's okay, not a big deal. You just need to be aware of which end is which when you're looking at it. So in this case, radio waves, or the longest wavelengths, are on the right. Gamma rays, the shortest wavelengths, are on the left. Okay. Big key idea here. Each wave type varies in wavelength. Okay. That's the primary difference between all of these, is the size of the wavelength. Okay. So that is the biggie there. I go back up to your notes. All right, I believe that was guiding question B and C. So you can answer those now as well. At this point, I'm going to pause and let you get out page 8 of your notes, and then we are going to go on and fill those in. Okay, I'm back, and I have up in front of you page 8 in your interactive notebook, and it's light lesson number 2B. I separated this out into 2B from 2A because visible light is part of the electromagnetic spectrum, but it's a whole separate topic, so I wanted to make it separate, okay? First off, guiding questions. A, we have, what happens to the light that strikes an object? B, what determines the color of an opaque, transparent, or translucent object? And why do light rays bend when they enter a medium at an angle? So that's what we're going to be talking about over the next few minutes. All right. All right, now going back to visible light. Visible light is the part of the electromagnetic spectrum that our eyes can sense. Okay, so again, going back here to the electromagnetic spectrum, visible light's right in the middle. That's the only part that our eyes can actually see. All right. So now there are 3 things that light does when it hits a material. So the first one, all right, type of material. On a translucent material, when light hits it, light is scattered as it passes through that material. And examples of those materials would be like wax paper or frosted glass. So that's like when you can hold wax paper up to a window and light will go through it, but you can't see completely through it. That means it's translucent. So the light is scattered as it passes through. Another thing that that happens to light as it hits a surface is that light can pass through it. And that type of material is called a transparent material. Examples of those would be clear glass, water, or air. Thankfully, air is transparent so that we can see straight through it. Otherwise, life would be more difficult. The third thing that can happen to light when it hits a material is that it can be reflected or absorbed. All right, and that type of material is opaque. All right, an opaque material will reflect or absorb light. Examples of those materials are wood or metal. Okay, so wood or metal is opaque. All right. So that was guiding question A. So guiding question B, what determines the color of an opaque, transparent, or translucent object? So I'm going to go to the screen. Here we have some different pictures of apples. We all know that most apples are red. With some, difference. Obviously, there's red and yellow and green, but in this case, it's a red apple. And here we have a picture of an apple, a red apple, with a red filter in front of it. And it shows white light, and it's white light because white light actually contains all the colors of the rainbow together all at the same time. So this is white light. And as it passes through this red filter, the only color that goes through it is red. All of the other colors are absorbed by that red filter. Because those other colors are absorbed, the only color that you end up seeing is red. Okay? The red light hits the skin of the apple and it bounces off into your eye and you see red. Okay? So here with the red filter, you see a red apple. Likewise, with this green filter, all of the colors are absorbed into that green filter except for green. However, the apple is not green. The apple is red, but there is no red light to bounce off of the apple. So you see the apple is being black behind that green filter. The same thing with the blue filter. All of the colors of the light have been absorbed into the blue filter except for blue. Well, the apple isn't blue, so the apple appears to be black behind it. Okay, so let's go back to the notes. All right, here we have blank light strikes the skin of an apple. All right, so this should be white light strikes the skin of an apple. And I could probably type that in. White light strikes the skin of an apple. Okay, then the skin reflects. So if it's a red apple, the skin is going to reflect red light to your eyes. That means that the apple's skin is going to absorb all other colors of the light. Okay, so you see the color that's reflected to your eye. All the other colors are absorbed by that object. All right, moving on to down here. We have two more examples. We have a red glass filter here. We have white light hitting it. And what I would like you to do is draw in two eyes here. My eyes look kind of funny, but that's okay. And so you have the red glass filter. You have white light hitting the filter. And what color is reflected back off of it? Okay, if it's a red filter, the color red is going to be bounced off back into the eye. Okay. Also, you're going to have red light pass through the filter. Okay, because it's just a filter. It's a translucent or transparent surface so that that light can go straight through it. All right. The colors absorbed all other colors are absorbed by that filter. All right. Over here, we have a solid green wall. So it's solid, which means that no light can pass through. All right. So the white light hits the green wall. If it's a green wall, what color do you think that we're going to see? We are going to see green light waves hitting our eyes. Colors absorbed by that solid wall are going to be all other colors are going to be absorbed. Okay. Now, the last part of the notes. So guiding question C. Why do light rays bend when they enter a medium at an angle? All right. So I am going to give you an example of that first. First, we have pictures here. There's a picture, two pictures of pencils sitting in glasses of water. And I want you to notice that the pencils are bent. Okay. So the first one is a refraction of light, or bending of light, makes these pencils look bent. So notice that, and then there's another one over here. Okay, the light, what happens is that the light slows down as it moves from the air into the water. Therefore, it causes the pencil to appear to be bent. So it's actually the light wave slowing down as it moves from the air into the water. And that alone causes the refraction of light, or it makes the pencil look like it's bent. The same thing happens through what's called a prism. The refraction of light through a prism splits the white light here into each of the colors of the spectrum. Raindrops in the sky act as tiny prisms, and they cause rainbows in the sky. Right? Same principle. So when we go back to your notes, scroll back down here. All right. We have refraction and why it happens. Sorry about that. So refraction and why it happens. All right. Refraction happens when light travels at different speeds through different mediums. And a medium is a fancy word for a material. So light travels at different speeds through different materials or mediums, and that causes light to refract or bend. All right. And there's one more diagram I needed to show you, and that is right here. Okay. And right here, I have an example of refraction and reflection. All right. This is also on your notes. This diagram here represents, sorry about that. This one right here represents refraction. It is light bending as it goes through a material. Refraction. Reflection is light bouncing off of a material. So this right here is light bouncing off of a material. Okay? And that is it for your notes. And have a fine evening.